Hello, everyone. My name is Alfonso Starain. I'm a CETES University student studying the major of Industrial Engineering, Global Program, sorry. And today I have my final project of Statistical Inference class, which this would be specifically focused on hypothesis testing. We first have a table of contents, which this includes a introduction, what is hypothesis testing, the f- we the first paper I chose, which would be the intelligent quality control in spare parts, and the hypothesis test approach on that same paper. Then for my second paper, I chose the neural network ownership verification, which we then continue with the hypothesis test there. After that, we compare both papers. We have the key takeaways from this project, and finally, a conclusion. Sorry. So, okay, introduction. For this project, we needed to select two papers, as you may already guessed, using hypothesis testing. These two papers we needed to get them from the Biblioteca CETIS, which is a digital um, library from our school, well, university. And in these two papers, we have a hypothesis test, which are in different fields. One of my papers is in manufacturing, and the other one is in artificial intelligence. What is the goal here? Well, my goal is to show how each study applies hypothesis testing to reach informed data-based decisions or conclusions. I'll also compare their methods and highlight how flexible and powerful hypothesis testing can be across disciplines. Here, I placed a little image of how well of hypothesis testing. This will be first I'm sorry, a right tail test, as you can see, a left tail test, and a two-tailed, which would be the middle part. Okay, so first of all, what is hypothesis testing? Hypothesis testing is a statistical method used to evaluate claims about a population using sample data. You start with two statements, which would be the null hypothesis, which assumes no effect or no difference, and the alternative hypothesis, which we H1. And this is what you suspect or want to test, the alternative hypothesis. We use sample data to calculate a test statistic, and we also use a p-value. If the evidence is strong enough, typically is being p greater than 0.05, we reject the null hypothesis and accept the alternative. And why we use this? This gives us a structured way to make decisions based on data, not just intuition. You can have two numbers and I don't know, one wins bigger than the other, and just by seeing them, you can assume that there's a statistical difference or it does make a decision on the data. But what we want here is a statistical difference. We don't want just by assuming or assumptions. We don't want any of that. We want a decision based on data or in here and hypothesis testing. Okay, continuing with what is hypothesis testing, we have the hypothesis testing helps reduce the risk of making incorrect decisions by quantifying uncertainty. The common test for this type of for this subject hypothesis testing, which would be a z test, a t test, a chi-square, and a nova, and etc. There are a lot more. We have two types of errors. Uh, the errors we need to consider are the type 1 error, which would be a false positive, and the type 2 error, which would be a false negative. What are the key steps to this? Well, first of all, we need to state the hypothesis. The null hypothesis, which be the assumption you're testing, and the alternative hypothesis, which would be H1, would be the claim you're trying to prove. For this hypothesis testing, we always have an alpha or a significance level. The most common choice is 0.05, which would be 5% chance of rejecting the null hypothesis when it's actually true. Then after that, we select a test and calculate a test statistic. Each of these, of the z, t, and chi-squared, have their own test, their own table, and so on. They're the same, but not the same. They're different. We use those. These numbers tells us how extreme our sample results is. Then we find the p-value. What is the p-value? As you may be questioning yourself, the p-value is the probability of getting a result as extreme as yours if the null hypothesis were true. If the p-value is greater than the alpha, you reject HO and we make a decision. If p is small, we reject HO, which that would mean the data supports H1. That would be we reject HO. And if P is large, we fail to reject, which there would be not enough evidence, not enough evidence to support H1. Here I placed I believe this is a t-table from one of the examples I gave you. We have the z-test, the t-test, and the chi-squared, and here it's a t-test. Well, not a t-test, a t-table. Okay, paper one. The first paper I chose or studied is titled Intelligent Quality Control in Spare Parts Production. This paper proposes a dual stage hypothesis testing method to improve how manufacturers decide whether to accept or reject batches of parts based on defect rates. The idea is to test small samples first, and if the results are unclear, we do a second one, which would be a larger test. This helps us reduce inspection cost while still making accurate decisions. The hypothesis test approach on paper number one. The objective would be to determine whether the defect rates of spare parts exceeds the supplier's acceptance rate or standard, which would be a 10%. We first, as I already mentioned, set a hypothesis. The null hypothesis would be we defect the rate if 10% meets, which would be it meets the supplier's standards, and the alternative hypothesis, which would be defect rates less than 10%. This would mean that it exceeds supplier standards. For our second step, we have the first stage test, which would be with a small sample, as I already mentioned. The small sample size here would be 52, and this would be that the decision thresholders accept if the defect rate is 5% and reject if the defect rate is 15%. And then we proceed to the second stage test if defects are in the rates between 5 and 15. Here, the second stage test, which would be with a larger sample, as earlier mentioned. And here our sample size would be 141. We combine the total defective items from both samples, which would be K total, which would be K1 plus K2, an easy formula. And the decision thresholders would be that we accept if total defects are greater than 10, and we reject if total defects are less than 20. The statistical tools we used a binomial distribution approximated by normal distribution. We apply a z-score standardization to calculate confidence intervals from 90 to 95%. Yeah. Well, why is this a binomial? We have a binomial because it's either accept or reject. And a z-score, is because of the confidence levels from 90 to 95. Okay, for paper number two. The paper number two I chose was the neural network ownership verification. This would be completely different from the one I just mentioned. This is a different world, literally. It's AI. It's titled the Invisible Watermark and Hypothesis Testing for Multi-Ownership Verification of Deep Neural Networks. Okay, what is happening in this paper? In this case, the goal is to prove who owns a machine learning model using invisible watermarks, like hidden signals in the training data. The cool part is that they do this using black box hypothesis testing. What does this mean? Meaning they don't even need to access the model's internal code, it's just the output. This makes it a lot simpler. The hypothesis test approach on the second paper. For our objective, we have to Yeah, we need to verify whether a deep neural network or DNN model contains a specific invisible watermark, providing ownership without accessing internal model details, which would be the black box setting. For our first step, as you may already guessed, we have a hypothesis test, which we have a null hypothesis. Sorry, what is the null hypothesis here? The model does not exhibit the watermark's target behavior, so this means it is not the owner. For the alternative hypothesis, we have that the model does respond to the watermark trigger. This would mean that it is the legitimate owner. We have two big verification scenarios, which would be a label-based verification that we'll be using a Wilcox test there. What does this mean? That this means the verifier only sees predicted labels from the model. We use the Wilcox, as I already mentioned, rank test to compare the predicted labels of original versus watermarked inputs. And if the p-value is below the thresholders, HO is rejected, which would mean the model is verified as the owner. For our second test, we use a probability-based verification, which would be a t-test. What does this mean? This means that the verifier sees the output probabilities of the target label. We use a one-tailed paired t-test to compare probabilities of original versus watermark inputs as the other one. And here, if the watermark outputs show significantly higher probability for the target label, HO is rejected, which this would mean ownership is confirmed. I'm sorry. Okay, why do we choose to test? Using both label and probability-based test increases the robustness and security of the ownership verification, and specifically under attacks like model pruning. This helps a lot to make it more secure, and we obviously want the best, the most secure verification. Okay, here we have the comparison between both papers. In paper one, I'm gonna be calling it the spare parts quality control, and paper two I'm just gonna call it DNN because the names are too big. Well, for paper one, the purpose was if we check if spare parts meet the defect standards, which would be 10%. And the second paper, we verify model ownership via watermark behavior. The hypothesis here would, in the first paper, would be that we defect if it is greater than or equal to 10%, and we defect if it is less than 10%. For our second paper, we have that no watermark detected, which would be in the HO, and H1 would be watermark behavior detected. Methods we used a dual stage testing, as I already mentioned, a small sample size first, which would be 52, and secondly, a large sample, which would be 141. In the second paper, we used the two black box test, which would be a Wilcox, which would be the one with the labels, and the t-test, which would be the probabilities. The statistical tools we used, binomial, because it's either accept or reject, the normal approximation, z-scores, and confidence intervals. For our second paper, we used a Wilcox signed rank test and a paired one-tailed t-test. The decision criteria for the first paper. As I already mentioned, it was accept or reject based on the thresholders and the 90 to 95% confidence interval. In paper number two, we reject HO if p-value is greater than the thresholders. Okay. For our first paper, the innovation, what does this helps? This helps on cost-efficient inspection through early filtering. And in the second paper, we have that the innovation part here is that the robust, secure verification of multiple ownerships using invisible watermarks. The applications, as you can already tell, are in the first paper is in industrial quality control, and the second one is in intellectual property protections for deep learning models. Key takeaways. Well, I'm just gonna say the main points. Both papers show how hypothesis testing supports confident, data-driven decisions, with which is what we're searching for. Paper number one focuses on efficiency in physical inspections, and paper number two focuses on security in digital environments. They both use different tools, like the z-score versus the p-value, but the core logic is still the same. We test, analyze, and decide. Hypothesis testing is not just academic, it's a real world tool for improving quality, saving costs, and protecting innovation. This, as you can tell, is a life, well, not here, but it can be a life or death situation. For example, what do I mean by that? This is the hypothesis testing is used a lot in medicine, engineering, and manufacturing. What do I mean by life or death? In medicine, a life or death hypothesis would mean literally life or death in a medicine or whichever. In engineering, it could be like I don't know, an airplane, a boat, or simply a car. If the hypothesis testing is not confirmed, we have a life or death situation, and we don't want that. We want the most precise, data-driven answer. Well, for my conclusion, I have that even though these papers are in completely different fields, they both prove that hypothesis testing is incredibly adaptable, as I already mentioned. And well, in the first case, it helped manufacturers make smarter inspection decisions. In the second, it helped protect the ownership of AI models. What really stood out to me here is that how something as structured as a hypothesis test can be used in such creative and practical ways. Like here, going from a factory lane to artificial intelligence is way beyond me, and I don't know how everyone does this, but it's incredible. And one takeaway, or in my conclusion, I have that this project really helped me, really showed me, sorry, that statistics aren't just numbers, and it's about making decisions that matter, as I already mentioned, life or death decisions. Thank you for your attention. I'll be seeing you on the next one.